Today we're going to be measuring the convection coefficient that results from the air being blown by this fan. As you can see, our experimental setup consists of the fan itself, some ice that has been in the freezer, and a timer to measure how long it takes to melt. The ice is being propped up directly in the path of the fan and is able to have the air blown over it over the course of the experiment. As after being placed here, the ice is then left to sit until it is completely melted, and then once it is completely melted, time will stop, and then we will use that time to help calculate the convection coefficient from the fan. So as you can see from this overview of the setup, it's pretty simple, but it's able to be this simple because of several assumptions that we're making about the situation. To begin with, we're going to assume that the bottom surface that the ice is sitting on is going to be adiabatic for the course of the experiment. Now, this is partially accomplished by the fact that the entire bottom area of this Tupperware container was contained in the freezer as well, so the ice or the air inside of it is also at the freezing point as well, or at a colder temperature. This way, the major temperature difference and the major energy transfer is going to be from the water to the air above it rather than to the air below it. Additionally, we're going to assume that all of the water in this setup is going to maintain at 0 degrees Celsius throughout the run. We are able to make this assumption because at the phase change where water and ice coexist, the temperature will be maintained as all energy coming in will be used to melt the ice and form liquid water. And finally, we're going to assume that any variations in the convection coefficient due to variations in laminar or turbulent flow are going to be negligible, and regardless, this is going to be a calculation of the average convection coefficient anyways. So, from the outset, this may seem like a transient process. However, because we're taking advantage of the fact that the phase change occurs at a constant temperature, we're able to simplify it greatly, and actually it turns out to be steady state. So as you can see, because the ice is the coldest part of this experiment, there's going to be no energy flowing out from it, so we are able to eliminate that term. And because the phase transformation occurs at this constant temperature, we are able to eliminate the right side of the equation and make it steady state. So we are left with energy coming in plus energy generated equals 0. Now what we find is actually energy generated, this term ends up being related to the enthalpy of melting of the water. And so because enthalpy of melting is in joules per gram, we're able to convert this by multiplying by mass to find the total joules, and then the rate is just divided by the time it takes for it to melt, which we are measuring with our experiment. On the other side, energy in is just our convection equation, which is, because we've assumed there are no temperature gradients inside, the entire surface is going to be the same temperature, then it's just the convection current times the surface area times the difference in temperature between the air in the room and the ice, or Ts minus T infinity. Now, as we rearrange this, we find that the energy from melting must equal the energy from convection, and therefore we can set these equal to each other. And through our measured data, we were using 1 tablespoon of liquid water, which converts to 14.79 milliliters or 14.79 grams, as water has a density of 1 gram per milliliter. The enthalpy of melting of water is 333.55 joules per gram, and the surface area of 1 tablespoon of water was measured as 0.00511 square meters. The temperature infinity, or the temperature of the air being blown over, was 74 degrees Fahrenheit, which is converted to 23.33 degrees Celsius, and of course the temperature of the melting water is 0 degrees Celsius. After rearranging the initial equality, we find that after isolating for H, we have the mass times the enthalpy of melting, over the time times the area times the difference between T infinity and T surface. We plug all this in and it simplifies down to 41,380 joules per meter squared divided by the time. And using these 3 data points of time that were collected over several trials, we can collect these 3 data points for the convection coefficient, or for an average of 55.88 watts per meter squared. In the end, there are going to be several points of error in this experiment. Mainly, the bottom of the surface is not going to be truly adiabatic. While it is initially going to simulate an adiabatic surface, the end result is that the air inside the container will also heat up and then will provide a source of energy from below as well as from above. Additionally, the water in the experiment is not staying perfectly mixed, so there may in fact be temperature gradients present. However, when we calculate the BO number, we find that the numbers work out such that with a 1 millimeter thick layer of water and a conduction coefficient of 0.606 for water, that any convection coefficient less than 60.6 will result in a BO number less than 0.1, so we are able to assume there are no temperature gradients present. And because of my inaccess to more precise measuring tools, I am using low quality measuring tools that will introduce error into the experiment, such as using the apartment thermostat for the temperature of the room, estimating the area using a ruler and other known areas, as well as estimating the depth for the BO number, and So in the end, based on my analysis of the error, I believe the calculated convection coefficient of 55.88 is going to be too high or greater than the expected value, mainly due to the heating from the bottom reducing the total time and therefore increasing the total convection coefficient. Yes. With further refinement of the experiment, this could be a valid experiment. With further refinement and more precision, this could be a very valid experiment for measuring the convection coefficient as a result of a fan blowing air.